Can you see it?
Yes.
Okay. Okay, so I'll talk about aiming for excited states, in particular double excited states with the pair couple cluster and orbital optimized pair couple cluster. So I have just submitted the paper with the results. You can find it on arXiv, the preprint. So in summary, pair couple cluster, PCCD, you restrict your excitation manifold to paired double excitations. So it's a simplified version of couple cluster doubles, let's say. And now we have this interesting feature that PCCD and double occupied configuration interaction used to perform all orders excitations, which preserve this pairing of electrons. So you always have open shell, closed shell. So you have this interesting matching of energies for the ground state of PCCD and the OCI. But now considering that PCCD has a polynomial scaling and the OCI has an exponential scaling, this is interesting, an interesting advantage for PCCD. Also, PCCD does a very good job in recovering static correlation. So it behaves very well for dissociating potential energy curves, for instance. And this is the concept that people usually have in mind is addition by subtraction. So there might be some cancellation of errors by restriction should pair the double excitations in PCCD such that you describe static correlation well compared with full CCD. And also it describes a minimum couple cluster based method for describing double excited states. So in the past, people have tried to model double excited states, for instance, starting with PCCD and doing equation of motion on top of it. And now here we're trying to approach it in a different way. So the main goals we have here are the following. First, how to target excited states with PCCD. It's not the same as doing it for ground state, so I have to be a little bit careful, and for that we explore the case of helium atom. And the second question is how does this nice matching between the energies for ground state compare for excited states, and how does it behave depending on the reference wave function you use. And then for that we studied the case of the linear H4 molecule and the symmetric dissociation of linear H4. And finally, how can we target double excited states with PCCD without making use of UM, and whether this is accurate or not, and for that to explore some larger, more realistic molecules. Okay, so in summary, as any couple cluster theory, you exponentiate your cluster operator on top of a reference wave function phi. And in PCCD in particular, we truncated to all paired doubles excitation. So you create, you annihilate 2 electrons in spin orbit I, and you create 2 on spin orbit A. And you do all combinations and have PCCD. And then you perform as usual, you project that into your reference and your double excited space, and you have an equation for the energy and an equation for the cluster amplitudes that you have to solve for, the T amplitudes. So you have, here it is, the equation for the energy, and then you have a set of K, which is the number of occupied orbitals times the number of virtual orbitals, equations, polynomial equations for the T amplitude. So you have a set of K equations for the T amplitudes that involve matrix elements of the Fock operator and 2 electron integrals, and I have to solve them for T's, and this is all coupled. Each single equation depends on all the other sets of T amplitudes. And now if you want to express the energy as if you want to minimize it with respect to some parameters, doing orbital optimization, for instance, then we have to build it as an expectation value. So I have to introduce the de-excitation operator, which de-excites. So it de-excites from one orbital to another. And then we express the energy as dysfunctional, and this gives rise to a set of also K equations. Now they are linear on the. So now if we impose a stationary condition for the functional with respect to the Z amplitudes, you immediately recover the previous equation for the T amplitudes and therefore for the energy. And if you do the same way for the T amplitudes, then you have a set, this is a set of equations for the Z amplitudes. So you can solve for these two sets of amplitudes. Now, we explore the case of helium in a small basis, so such that we can solve it analytically. So this is the residual, which is basically the equation you have to solve for the amplitudes as a function of the T amplitude. So when it's zero, this is a solution of your set of couple cluster equations. So this represents the ground state, and this represents the excited state. And another way of seeing this is translating this as a extreme problem. So a problem, instead of finding for the roots, you're trying to look for minima or maximum stationary points of the integrated residual. And usually what people do is the algorithm for solving, for finding these roots, is based on an assumption that the Jacobian is diagonal and constant. And in doing so, you're always trapped into going to the ground state. So even if you start very close to the excited state, in this picture, you'd always go down in this curve. So you either diverge if you start here, or you converge to the ground state. So this already illustrates that the usual algorithm wouldn't work, and you have to provide the actual full Jacobian in order to target it for excited states. So that's what we did. We do Newton-Raphson algorithm with the information of the full Jacobian. And as I said, for ground states, it's usually fine doing a diagonal T-independent approximation based on the orbital energy differences. But for the states, you have to use the Jacobian because you needed information about the actual curvature of the residual equation as a function of the T amplitudes. So here, just showing the expression for the diagonal, and you see that okay, this is the usual approximation, and then you have other elements, and in particular, it's dependent on the T amplitudes. So you have to know where you are in your amplitude space in order to update it accordingly if you're targeting for an excited state. And this doesn't represent so much of a burden in terms of time, because you already perform all these contractions here for during the residual equations in the first place, but it does have an extra cost in terms of memory. But in any case, for the systems we have explored here, this is minor, and we can compute and invert it, and it usually always I would say converges at fewer iterations. And then for the Z amplitudes, they are linear, so Newton-Raphson step is exact. So this is also a nice feature using Newton-Raphson. And then, okay, we're doing orbital optimization, and for that we introduce this kappa operator, which performs all, it interchanges orbitals P and Q, and then once you exponentiate that, you perform orbital rotations and you preserve the orthonormality of your orbitals. And then with the previous expression for the energy functional, we introduce the exponential of the kappa, this orbital rotation operator on the left and on the right of the Hamiltonian. And then we have an energy functional which can be minimized with respect to kappa, or with all kappa parameters. And what we do again Newton-Raphson, but now for orbital optimization. So basically we expand it up to second order around the kappa equals 0. And we do a Newton-Raphson step along this direction, which is the direction that minimizes this approximate energy functional. And then this resets your orbital. Now you have a new set of orbital, a new reference, and you perform another second order approximation and do it iteratively in an iterative way until the orbitals are converged. So in summary, this is the picture of how we run orbital optimized by a couple cluster. So we start with the canonical hydrophilic orbitals, let's say. You can change the occupancies of it if you're targeting for an excited state. And then we solve the couple cluster equations based on information on the Jacobian. Once we solve for it, we build up the 1 and 2 electron density matrices, which gives us also orbital gradients and the Hessian. And then with that, we do a Newton-Raphson for the orbital optimization. And then for each step, we have the exponentiation of the kappa vector, and then we rotate the orbitals. This sets a new reference, and we do it again. We solve again the couple cluster equation, and we do it until the orbitals are converged. So this picture here, I mean, the more you look at it, the more you learn about. I mean, there are lots of interesting things to look at here, but I'm showing, okay, so on the left, I'm showing T amplitudes as a function of this kappa, single kappa parameter for the case of helium. It's a 2 electron system with this base, you have 2 orbitals. And then on the bottom, I'm showing the energy, right? Again, as a function of kappa. And then here is just a zoom into this region around the T equals 0 here. And here's a zoom around this, this very sharp avoided crossing here. So you see, for instance, around kappa equals 0, which is defined by the Hartree-Fock orbitals. We have 2 solutions. We have a solution with a very small amplitude, which corresponds to ground state here. And then we have a higher solution, which corresponds to a very large T amplitude, which is the excited state. And then here on the right, I'm showing the difference between per-CCD and full CI energies with respect to kappa again. So you see that the energy is rather small for Hartree-Fock orbitals, and then when you optimize for when you optimize orbitals for per-CCD, it eventually matches the full CI energy as we expect for the case of 2 electron systems, and the same way for the excited state. So for excited states, for instance, if you simply change the occupancies and put 2 electrons on the unoccupied orbital, you start with kappa equals 90. And then when you optimize for it with Newton-Raphson, then you go up on this curve, and we finally reach this stationary point, which matches full CI energy. Right? And then another thing is, okay, so this is the exact energy for the ground state. It is the exact energy for the excited state. And you see that if you are far from either kappa equals 0 or kappa equals 90, your reference is extremely poor, and per couple cluster cannot do anything to recover on that. So this also shows the importance of having a good reference when aiming for either whenever it's either state. So now moving to H4. So here it's linear H4, and we're stretching it along the distances between the hydrogens. It's a symmetric stretching of the molecule. So it has 6, a ground state, and then 4 doubly excited states and 1 quadruply excited state. And here I'm showing the comparison for the potential energy curves obtained with per-CCD computed with the ground state Hartree-Fock orbitals, and then DOCI computed with the same set of the same Hartree-Fock orbitals as points. So the first result here is that the energies don't match for the excited states. They do for the ground state, which was expected, but not for the excited states. And this is the fact that the orbitals were obtained for the ground state. And once you use them for the excited states, then you no longer expect the energies to match. And in particular, you see that for the first excited state, you have the appearance of 2 solutions. So we have discussed this before. And then also for the third excited state, here you cannot see very well, but there are also 2 solutions, 2 real solutions that at a given point merge into a pair of complex solutions. And now when we do orbital optimization for each state, for each specific state, then we see again a very good matching for the excited state. So this is also one of our main results. Like when we have a suitable wave function describing an excited state, then per-CCD and the OCI provide very comparable energies again. And then also you see that this complex solution that appeared before disappear once you optimize for the orbitals. So that's like an artifact that's simply because the reference space, the reference wave function was not good enough for describing that excited state. And then you can understand this difference based on the fact that PCCD does not have higher connected excitation. So in particular, quadruplet excited connected excitations are missing PCCD, but are present in the OCI. And they become important when the reference is bad, which was the case here. So your reference for the excitation is very bad, so you have to introduce lots of higher order excitations in order to have a better description of it. So they are important, and they appear in the OCI, but they don't appear in PCCD. So this gives this large difference. But then when we optimize the orbitals, now the reference is good, and then you don't have to account for much for higher order excitations, because they would introduce only some residual correlation effects. So double excitations would be the most important, and they're present. Connected doubles are the most important, and they're present in both the OCI and PCCD. And then this explains the good matching for the energies in this case. So here is just the two figures again. And now there is one detail here, is that we only looked at symmetry preserving solutions. So all the orbital rotations preserved the symmetries of all states. So if we checked, for instance, the number of negative Hessians along the curves for each state, we have these numbers here. So for the ground state, for instance, it's 0 elsewhere, everywhere except for some intermediary region where it has one negative eigenvalue, which means that there is one lower line symmetry broken solution for the ground state. And you also see that for some excited states, the number of negative eigenvalues change at one given point, which might also be a clue that you break symmetry for some of these excited states. But again, for the purpose of comparing the OCI and PCCD energies with orbit optimized reference, the symmetry preserving solutions are good enough for this. So here's just to show the large improvement that we have once we optimize for the orbitals. So this I'm showing in dashed here are the energies, are the energy differences between PCCD and the OCI for Hartree-Fock orbitals in dashed lines, and for the solid lines for orbital optimized orbital. So you see large improvement for all states, in particular for the quadruplet excited states. So yeah, so the energies now are much closer once we optimize for the orbitals. And this is just to show on the left the energy differences for PCCD with and without optimizing orbitals, and on the right the same, but for the OCI. And you see that the dependence on the method with respect to the orbital. So it's much less for the case of the OCI than with PCCD. And now going to the final part for larger molecules. So we explored 5 molecules with a small basis set, and yeah, we implemented the orbital optimization and did the OCI calculation on quantum package. So here I'm showing some vertical excitation energies for the systems, for the double excited states of the systems. So the main things here are the following. So for PCCD with the Hartree-Fock orbitals, usually we are way off with respect to the reference values, which are, of course, full CI. So you see here that it's off. Here in the case of BH, it's 10.8 versus 7 in full CI, it's way off. But once we optimize for the orbitals, once we do a state-specific orbital optimization, which means that we do orbital optimization for one state, then we do a second separate calculation with orbital optimization for this particular excited state, and then we compute the energy difference. So this is this delta OOPCD. Then we have a much better agreement with respect to full CI. So you see here massive improvement, also here in the case of BH. And it also compares very favorably with the other more computationally demanding methods such as UM-CCSDT and other UM methods built up on top of PERCCD. So going to slightly larger molecules on nitroxyl, nitrosamethane, formaldehyde is the same story. So in particular here for nitrosamethane, we couldn't even locate an excited state, a double excited state with canonical hydrophilic orbitals, or perhaps we did, but extremely way off in energy. But then again, when we optimize for the orbitals, then we find the state and it compares very, very nicely with full CI results. So despite being small set, 5 molecules, and only with a small basis set, so we computed some statistic quantities. So we have root mean squares very close with respect to UM-CCSDT, for instance. So it's the accuracy of the two methodologies are comparable, and it's much better than CC3, for instance. But then again, this only works when we optimize for the orbitals. PERCCD with canonical hydrophilic orbitals are totally off. And for the 3 larger molecules that I showed here, again, it's a small set, but with PERCCD, we have more accurate energies with respect to full CI than UM-CCSDT. Okay, this is might not be the case if you explore larger molecules, but we seem to have a better agreement for the case of these larger molecules. And then there's also one interesting feature that since the reference is built up in a separate way for each state, you don't have a bias for the ground state as you do with UM, for instance. So correlation effects are introduced in a more balanced way when you do PERCCD. And we can wonder whether this is desirable or not, because of course, if we know that we are biasing towards the ground state, and correlation effects are introduced more slowly for the excited state, you'll always be above the real value. So as we go up in excitation order, for instance, you know that we're approaching the exact value from above. But that's not the case for if you state-specific orbital optimize your reference, because now both are equally good, and correlation effects are accounted for more balanced way, and you might be either above or below the full CI result. That's what we also saw for this set. And overall, doing this delta OPCD might be an alternative method for targeting double excited states. The errors here with respect to full CIs are pretty small and comparable to other methods. So the main conclusions we have here are the following. First, if we are going to target excited states with PERCCD, you cannot make use of usual algorithms. They will not work. You have to actually provide the Jacobian or some approximation of the Jacobian, but you need some information about the curvature with respect to the amplitudes when solving for the couple cluster equations. And you have to provide, again, even if in approximate way, but the Hessian, the orbital Hessian, for performing the orbital optimization. Otherwise, you will converge to the ground state solution, and that's not what you want. Now, the second main conclusion is DOCR and PERCCD can still provide very comparable energies for the excited states, but only as long as you build a good reference for the excited states. And we do this by orbital optimization. And this method is delta OPCD. We saw that it does provide accurate energies for the double excited states, even though the set is still small. So there are many open questions that you can explore. So maybe from more specific to more general, they would be the following. So you notice that for the potential curves for OPCD, they ended at one given point. So we faced some problems in convergence. So what's the nature of this convergence problem? So perhaps it's the algorithm. Perfect. There's one thing that we should still do, which is to generalize Newton-Raphson, I mean, doing trust region Newton-Raphson, so probably that might improve the convergence in general, and we might find some solution that is still missing. Or it could be that you simply don't have solutions, stationary points which are real, and perhaps the orbitals should go complex, so such that you find a solution. Or it could be a failure of PTEROSOR itself. Perhaps it simply fails to locate a solution for that state. Another thing, of course, is how does the method compare for larger basis sets? How does it perform for larger basis sets and for larger molecules? So we saw here a very good performance for small basis set and small molecules, but how about more challenging systems? And how can variational pair-couple cluster improve with respect to PTEROSOR? And here we can also wonder about the use of orbitals. So we can use Hartree-Fock orbitals or MOM orbitals, or optimize them for PTEROSOR, or perhaps optimize them for variational PTEROSOR and see how they compare with respect to FUCI or with respect to the OCI. So there are many combinations that we can explore here. So this connects a lot with what Antoine is doing right now. So he's studying H4 square H4, for instance, with variational PTEROSOR, which of course should be more accurate than PTEROSOR. And the other question is, how can we generalize PTEROSOR to target single excited states? So, I mean, we could simply try to add the singles excitation on your ansatz, or you can try to do EOM, and in which then you introduce singles in the excitation operator. I mean, this is challenging because we don't want to actually CCSD if we want to try to keep these interesting features of PTEROSOR concerning this good recovery of static correlation, for instance. So we should think about how to include single excitations if you want to target for single excited states. And one other thing was, what about the strongly correlated systems, which of course is much more challenging. So for all molecules that I showed here, they are weakly correlated molecules, and we expect that PTEROSOR would perform rather okay and actually very, very favorably in this case. But what about strongly correlated systems? And so Antoine is also doing something in this line. So he's exploring square H4, as I said, in which you have some more strongly correlated case. And I think that's all. I end up here.
Thank you, Fabris. Sorry, I was muted.